welcome back to Math with Patrick. It's March 21st, and we have problem number 80 from that Daily Epsilon calendar we've been working on. And the answer is 21, which is today's date. Find the coefficient of x squared in the Taylor expansion of this function at x equals 0. Okay, what does this all mean? This function, f of x, I noticed that it's some kind of exponential function. It's kind of like e to the x, although it looks like our exponent is even greater than just an x. So whereas e to the x kind of looks like this, I'm assuming that our graph, since the exponent here is bigger, it'll kind of scoop up really, really fast. And a Taylor expansion, that's going to be some kind of polynomial approximation of this curve. And so just a little review of polynomials. You could have a degree 0 polynomial, which is basically just like a constant. You could have a degree 1 polynomial, which basically means you have some kind of x to the power of 1. But again, power of 1 doesn't really do much. Then you could have a degree 2 polynomial, and those are going to be things that look like quadratics, something like this, or a degree 3, degree 4, etc. And the more polynomials you tack on together, maybe you're going to add, maybe you're going to subtract, the closer you can get to approximate any function. So the first term in our Taylor expansion is just going to be a constant polynomial, and it's essentially just going to be this y-intercept here. That's what it means for a Taylor expansion at a certain number at x equals 0. We're going to be looking right here and trying to approximate the curve as best as we can with just a straight horizontal line. So not that good of an approximation. Then, once I'm able to add on the linear term of my Taylor expansion, I could get this value and then match the slope of the curve. And so here it's already a slightly better approximation. Of course, it doesn't really match later on, but at least in the neighborhood of x equals 0, it's a pretty good approximation. Then once I find some kind of parabola or quadratic to add on or maybe subtract from my sum, I want to get something that might look like this, and it'll be an even closer approximation of my function. And we're just going to keep doing this over and over until we get some kind of x squared term, I guess. Oh, and that's actually going to be the quadratic. So we need to do 3 terms in this Taylor expansion. So first thing to set out is, what is that initial horizontal value? That one won't be too hard to get. F of 0 is going to be e to the power of 3 times 0 squared plus 6 times 0. That's basically just e to the 0, which is 1. So I can draw a little sketch on the right side. I'll just redraw the same thing. We're going to have some kind of curve that scoops up really, really quickly. And it's going to have a y-intercept at 0, 1. Cool. Now I need to know what that linear term of my function is going to be. So this is where derivatives are really helpful. Derivatives and slope kind of go hand in hand. So I'm going to try to find the first derivative, and that's going to inform me about the slope. So looks like I'll need some chain rule ideas here, because I have a function inside of another function. So the derivative of e to the x is just e to the x. That's a kind of fun feature here. Its slope is always its value. So for my derivative, I'll do e to the 3x squared plus 6x. And then the derivative rule, called the chain rule, just states that once you have a function on the inside of another one, you need to multiply by the derivative of the inside function. So I'm going to employ the power rule here, and I'll take the derivative of this. Power drops down as a coefficient, and it would be to the power of 1, but I don't really need to write that. And then the derivative of 6x, that's just asking how is 6x changing, and for every 1 you hop over, it's going to go up 6. So the derivative of 6x is just 6. Great, so I have my first derivative, and I need to know its value at 0. So f prime of 0 is, okay, well I have e to the 0 again, so I'll just do that really quickly. And then times, and then it looks like the 6x, when I plug in a 0 here, it will be 0. So 0 plus 6 is 6. So my first derivative evaluated at 0 is the number 6. Got it. So how should I draw this on the graph? I guess I could draw a line like this, and then I know it's not to scale because a slope of 6 would be super steep, but I'll just say m equals 6. M is usually a variable for slope, and then now I have an idea of my position at x equals 0 and now my slope at x equals 0. So then finally, I need to find something about the curvature of this curve, this function here. And the second derivative is a great resource to talk about the curvature. So I'll just take a look at my first derivative and try to use that to get my second derivative. Well, I see we have a product. We have two things being multiplied. And we also have chain rule. We also have the e to the x. So let's just use all those rules again. So thinking about the product rule overall, I like to think of it as the derivative of the first times the second, just as is. So this will be a 6x plus 6 plus the first times the derivative of the second. And so this one will just go right there, exactly as it is right here. Okay, derivative of the first. We already took the derivative of this. That this is our function, and so I know that the derivative of our function is just going to be this guy right here. So I think just for being concise, I don't have much space here. I do know that this is going to be just f prime of x because I'm taking the derivative of the first part, and we already did that. So this isn't what the product rule says, but this is just an interesting feature based on the function that we're currently working on. I can be a little concise and just put f prime of x right there. And then the derivative of the second part is just going to be 6, because the derivative of this is 6, and that is 0. So 6 plus 0 is 6. Okay, so now I have my second derivative. And again, I want to plug it in at 0 because that's the x value that I am concerned with. And let's see, f prime of 0, we already said that was 6. Plugging in a 0 here, I get another 6 because 0 plus 6 is 6. Plugging in a 0 here, I get a 1 because that's kind of what we already saw from the very, very start. And then, it's 1 times 6. So the second derivative here is going to be 36 plus 6, or 42. All right. And that's as far as I needed to go because we're thinking about that x squared term in the Taylor expansion. So let's think about that. F of x is going to be approximately equal to, we're going to take the value here, 1, because that gives us that horizontal line. Then we're going to add on a plus 6x because that approximates a slope. And then it's not going to be a plus 42x squared. Because I guess if you imagine using that power rule again, and you imagine taking the derivative of this part, we're going to get like an 84x. And essentially, you need to compensate for the fact that this 2 would come down if we took its derivative. So when you're doing these Taylor polynomials, there's a formula for it. Once we find the value of the second derivative, we're going to divide it by 2 factorial and then multiply it by x squared. So actually, secretly over here, it was going to be f prime of 0 over 1 factorial times x. And then continuing this pattern, we could do the third derivative at 0 over 3 factorial times x cubed. And this dividing by 3 factorial, you can kind of think of it just as the fact that once you do the power rule on this x cubed, this 3 would come down and then the 2 would come down and kind of cancel out with that factorial in the bottom. So actually here, just to write the general form, I'm going to do f of 0 here. And then knowing that we only need to know the coefficient of the x squared term, I don't really care about the x cubed term. And then now I'll plug in all the numbers that I got from earlier. Here's the 1, Here's a plus 6x. Again, it's 6 over 1 factorial, but 1 factorial is just 1. And then finally, we get the plus 42 over 2 factorial. That's just 2 times 1, or 2, times x squared. And this is the number that we're trying to find. This is the coefficient of the x squared term in the Taylor polynomial, and that is going to be 21. So we're all done. That is how you can find the answer for today. And let's hop over to Desmos real quick, just to show visually how what we just found actually does approximate the curve. Our function was f of x equals e to the power of 3x squared plus 6x. So kind of like I was thinking, it does scoop up really, really quickly, really fast. Although I didn't actually predict this left side. I didn't realize it was going to also go back up that way. And let me change my x scale a little bit just to widen it, or actually zoom it in a little bit. That way we can see more detail here. So our Taylor polynomial started with a 1. And so here's that horizontal line. It's getting the exact value of our function, the f of x function, but it doesn't really approximate it that well at all anywhere else besides just this one point. Then we found our first derivative and found that 6x term. And now you can see, if you zoom in the neighborhood, that blue line basically perfectly approximates the red curve. Again, only in the neighborhood. If you zoom out, it's not really that good of an approximation. So adding on that 21x squared improves the approximation even further. If you zoom in, there's more of a I guess, range, or more of a interval that matches the parabola to the red curve. So there's going to be some kind of x cubed term that we could add on that further improves this approximation, kind of just based off of these numbers. It'll probably be somewhere around 40. I can't quite tell, but that was a good guess, because see how it matches this back part of the curve a little bit better. And you could keep doing this. Again, you aren't supposed to approximate it. You're supposed to use calculus and find the values. But if I get maybe 120, that might have been too big. But it's going to further and further approximate that red curve even and even better. So we don't really need these terms for the problem today. This parabola generally approximates our red curve pretty well in this neighborhood. And this 21 matches today's date. So that's all from me today. Thanks for coming along, and I'll see you in the next video. Okay, bye.